Good morning. Welcome to day 2 of calculus. If you guys could open to the big packet, page number 10. We'll start there. I'll talk about the homework and where it's supposed to go, and I'll talk about the green folders, but I think there's a couple of people that just aren't here quite yet, so we'll wait a few minutes on that. But on page 10, we're going to spend a little bit of time on this activity. It says about 15 minutes. First, can we get a reader here? Can we go with Gary? Can you just read this intro? Okay, everybody understand what's the horizontal axis? That's time. You can see the little t there. That's how many hours. What's the vertical axis? That's the distance that they've traveled in miles, okay? Distance is a function of time. So there are a whole slew of questions, a couple at the bottom and a bunch on the next page. So work with each other. If you get stuck, raise a flag and I'll come over and help if I can. We'll spend about 15 minutes, but see if you can get through everything on this page and the next. So before we talk about the zombie race, which I know you're dying to do, thank you. Let's just do a couple of logistical things. So first, everybody grab a copy of the studio bookmark. It's this green bookmark I put on your desk. This tells you exactly when the studio right across this hallway here is covered. So in particular, you should note that before our class every day, Jen is going to be over in that room from 8:10 until 8:40. So that's a good half hour to get questions answered, but there are a lot of other times when we're covered, so take advantage of the studio. Also, I don't know if we said this the other day, I think we did, but there is a solutions manual in the studio for your textbook, every problem worked out in full detail, not just answers, but step-by-step process, okay? That's a good resource. It's right in the bookshelves across the hall. Next, if you don't need to take a look at this instant, but I'm just pulling it up. On our syllabus was a little section about YouTube, and there are a couple of links. If you go to that second link, it will pull up this page right here. So some of you may have noticed that I've had a Bluetooth in my ear last class, and I have one now as well. I record all of my classes. I record the audio, and I record the video, everything that happens up on the smartboard. If you pull up my channel by going to that link, you'll see a whole slew of videos for all of my classes. If you know what the format is, it'll be really easy to find what you are looking for. So for example, the class that we had last time was on September the 5th. That's all you need to know. If you're looking for a particular class, you just need the date and the format. So here's the format, and this is also written on the syllabus. But right there, all right, it's kind of confusing because it looks like 2012, that's the year, and then 012, which is kind of meaningless. All right, it's unfortunate that the year happens to look so close to the course number, Math 201. That says 201, that's you guys. 2012 is the year. September 05, notice the 0 in the date, it's a 2-digit date. If you click on that video, and we'll pull this up, and I'm just going to fast forward. That's fine there. Where's most ends at 4 degrees? Is something you guys do? So you hear the audio anytime something happens up on the screen, including moving the calculator or writing things up. Now let's see, we can go back a little bit, and I think we'll see writing. Hello. So much drama. It's like riveting, right? You don't even need TV after. Okay, so just know this resource is here. I expect that the videos will be posted before noon every day that we have class. So you can go and check out, and you know, as you're studying for our test, which is like infinitely far away at this point, but you know, if you say, oh, I really had trouble with that concept of the derivative function, just need to know the date, September 14, and then type in the format. Any questions on that? Okay, so let's come back to our zombie race, and we'll just talk strategies here. What was Feynman's running strategy? Slow but steady. How about Hertz? Okay, so we're constantly accelerating, right? We were going kind of slow in the beginning. We didn't cover a lot of distance in the first hour, but in the second hour, we covered a little bit more distance, and then speeding up to a sprint at the end. And then we come back here to Noether. What was her strategy? Was going to go kind of fast in the beginning. We covered the most distance in this first hour, and then slower to the end. And then Planck had a more complex strategy in the beginning, really fast, like sprinting in the beginning, and then so several groups said break for zombie brain eating, and then at the end, right, you use the newfound energy and you sprint again. And so you guys did a lot of stuff with average velocity, and maybe we didn't think about it, but I'll highlight it here. Suppose that I wanted to find the average velocity for an author for the first 2 hours. I think what the different groups did is we went and said, okay, let's see, 2 hours is here, so we'll jump up to there. And the vertical line represents what? The change in distance, right? That's how far she ran in that time. The horizontal line is a change in time, and if you divide them, you get the velocity, right? Change in distance over change in time. I'm going to draw something, though, something that you weren't required to draw, but I'll draw it here. I'm going to draw that line, extending in both directions. We'll just make up some numbers. The change in distance, to me, it looks like it's about 2.6. Change in time, 2 hours. So when you guys said the average velocity here, and you might have had a slightly different number, something like 2.6 over 2. What does that have to do with the blue line? That is the slope of the blue line. Yes? And just if we forget all the velocity stuff, I could just say find the slope of that line. What would you do? Well, exactly this. Rise over run. So what does that mean? It means that average velocity is a slope. And when you have a line that connects 2 points on a graph, we call it a secant line. We'll see this definition today. But this is just sort of a preview of what we're going to do today. The average velocity is the slope of a particular line. And that leads someplace good, because if I were to, for example, let's do this one right here. Let's see if we can estimate the instantaneous velocity. At t equals 3 hours. So a bunch of groups came up with the really, really good idea to say, okay, I could find the average velocity between 0 and 3. I could find the average velocity between 2 and 3. I could find the average velocity between 2.9 and 3, and really whittle down and get down to this sort of tiny fraction of a moment, which is the moment we're interested at exactly t equals 3 hours. And that's super. But how would you do it if you like the numbers, like if I said, all right, so that's the point I'm interested in. Let's pick this point right next to it and see if we can find the change in distance over the change in time. Well, all of those numbers are nearly identical. So how would you do it? You're going to do it by thinking about that blue line that we drew over there. If I wanted 0 to 3, I would draw this secant line. If I wanted 2 to 3, I'd say, okay, I'm going to draw that secant line. And if I keep drawing, eventually the secant lines kind of, I don't know, they sort of disappear, I guess, at the one instant when the point is right on top of the other point. But it's got a name, and I'll draw it here. Anybody know the name of the line that just sort of barely grazes the curve? That's a tangent line. And so what we're going to see today is that the instantaneous velocity is the slope of the tangent line. And I can estimate the slope of that line. I mean, it's just a ballpark. The line I drew was a ballpark, but I'd have a hard time doing change in distance over change in time with 2 points that were almost on top of each other. But I can estimate the slope of that line. And tangent lines are going to be at the heart of this course.
Why is the other line a secant line?
Why is it a secant line?
Yeah.
I'm not sure what what are you asking right now?
Why is it?
Yeah, like if you have a line that you're connecting 2 points on the curve, that is called a secant line by definition. If you have a line that just barely grazes the curve at 1 point, so if I wanted to draw the tangent line at this spot, I want it to hit, and then it's sort of hard to tell, but sort of run away from the curve up at the top. That's called the tangent line, the one that just barely grazes at the 1 point.
Yeah, I get that. I'm trying to think of it in terms of like, that would be like 1 over x or 1 over y.
Okay, so you're trying to relate these words, secant and tangent, to the trig words, secant and tangent. Good question. Maybe we can tackle that a little bit later when we go, when we talk about the trig functions. We have a day we're going to review the trig functions. But the one thing I will say is, I think we can say this. So a very, very quick review, and if you missed some of this, that's okay. This is our friend, the unit circle. And if I were to draw this guy right here at some angle theta, you guys remember the definition of the tangent? Okay, so we have actually a whole slew of definitions, and we just heard a bunch of them. So I heard opposite over adjacent. Great. I heard sine over cosine. Also great. If I call this point right here x and y, and the radius of that circle is r, but how much is the radius of the circle? It's 1, if we drew the unit circle. Does anybody know the x, y, r definition of tangent? It's y over x. Yes? Okay, it turns out, let's come back here, that if we were to extend this guy until it's directly over the right-hand edge of the circle, and I were to look at the length of this thing right here, it turns out that, if I were to look at the length of this thing right here, it turns out that that is the tangent of theta. The length of that line outside the circle, which is weird to look at something outside the circle, but it turns out that the tangent of that angle is this vertical length right here. And what kind of a line would you say that blue line is for the circle? It is vertical, but how many times does it hit the circle? Just once, just barely hits it. And what are we calling something that just hits the curve once is a tangent line? So there is some rhyme and reason to the names. Good question.
Secant would be r over y.
Secant is also up in this picture. I don't have a connection for you for the 2 points.
Yeah.
Okay. All right, let's jump to the next page. We're here on page 12. Oh, you guys have folders on your tables. What you're going to do for me is put your homework and questions of the day and everything into that folder when you get here first thing. So if you haven't done so yet, put your stuff in there. Because this is the first day we're seeing the folders, what you're going to do is claim one of those rectangles to just sort of keep your own attendance for the semester. So today, write your name on at the top of one of those rectangles if you haven't done it yet. And then every day you get here, you record the time that you arrived, okay? I'm not looking for check marks. I'm looking for, oh, we got here at 8:30 today or 8:45 or something like that, all right?
Here or the studio?
Either way is fine. Either way is fine. That's fine. Okay, so let's go to number 1, and I think we're at, who was our first reader? Gary was our first reader. Lindsay, can you read number 1? Okay, so here's a formula that that maybe you've seen in some physics-y type class before. It tells you how high something is at any moment in time if it's falling. So let's see if we can fill in our specific numbers for this formula. So I've got a 1/2. A is the acceleration due to gravity. We are in metric because we're doing meters here. Anybody happen to know this magic number? Yeah, it's about 10. I'm going to call it 9.8. 10 is probably close enough for most of our purposes. You see a little space in front of the 9.8 there? You know what we're about to put in there? I'm not going to put a variable. In which direction does gravity pull? Down. And we're going to call up positive, which means down is negative. So we're putting a negative in there. If we don't put the negative in there, the ball is just going to fly up forever and ever and ever. All right, so there's t squared, and then we have plus v0. That's the initial what? Velocity. All right, let's see. Instantaneous ball is, all right, so there's one word here that tells you the initial velocity is dropped. Initial velocity is 0. That's 0 times t, highlighting the 0, plus, for some reason we use s for height. So S0 is initial height. How much is it? 450. Yeah, 9.8 is a constant. It's the gravity here on Earth. Okay, so we'll just clean this up. S of t is negative 4.9 t squared plus 450. Okay, so we're trying to find instantaneous velocity. We don't have a picture to draw on in this one. We just have a formula. So this will be the same idea, but it's a different technique. All right, you want the velocity at t equals 5. What we're going to do is hone in on that moment t equals 5 by doing a lot of average velocity calculations. So for example, let's see if we can find the average velocity. And I'm just going to put here between 4 and 5 seconds. That's how I'm going to write. I'm going to try to get close to 5. We can't get exactly at 5, but let's look between 4 and 5 seconds. So our basic calculation is always going to be change in distance over change in time. That's what we know. Average velocity, change in distance, s, over change in time. So in terms of symbols, what I want to know is how high is the object 5 seconds in? How high is the object 4 seconds in? And what are we going to do with those two numbers? We're find the change. We're going to subtract those two numbers, right? So in terms of those symbols, I can do s of 5. That's how high the ball is 5 seconds in, minus s of 4. That's how high the ball is 4 seconds in. Divided by, it's going to be 1. I'm going to write 5 minus 4 just so we start to kind of see the pattern. But things are always going to look like that, where it's almost the same up on top. Just on top is our function values. All right, now we need some calculator help. So some folks find what you get when you plug 5 into our blue formula here. Some other folks find what you get when you plug in 4. And if you have either of those numbers, just shout them out. $371.6. Okay. So 5 seconds in, the ball is at 327.5 feet. Or meters, sorry. 4 seconds in, it was higher than that. Does that make sense? Which way is the ball going according to those numbers on top? Yeah, it's going down, right? Because later into the experiment, it was lower than earlier in the experiment. Okay, so what do we get when we subtract here? $44.1, thank you. And that's still divided by 1. So negative 44.1 meters per second. And I'm hoping the units make sense. All right, so it's a velocity, meters per second makes sense. But what were the numbers on top? The 327 was what? Was meters, right? And the 5 and the 4 on the bottom were time in seconds. So the units agree with what they were. Okay, so maybe roughly we could say it's falling at about 44.1 meters per second. At least that's what it's doing in this interval. But let's zoom in even more. Average velocity, let's go between 4.9 and 5. So can you guys start by writing something like that first red fraction? I'll go to the calculator at the beginning, just sort of get used to the notation. You could go 4.9 to 5.1. Yeah. The standard way of writing some notation that we're going to see is to not go a little bit above and a little below, although you could, is just to go from the moment you're interested in to a little bit away. Yeah, but absolutely, 4.9 to 5.1 would give a slightly different answer, and it would be just as good as the one we're doing here. Okay, so hopefully we've written something like that. And we do some calculating. Anybody want to share any of these numbers? I'm going to do the first one in my head, 327.5. Thank you. What was the end? 2.5? 3.5. Okay, and then when we subtract upstairs, what do we get? 4.85. Am I right? Yeah. And what do we get when we divide? So we had a 1/10 of a second that passed, and in that 1/10 of a second, the ball fell 4.85 meters. So if I were to kind of get this to be a nicer number, what would I get? It's just one nice number. 48.5 meters per second. And this reminds me of that, it reminds me of the soccer thing that we looked at the other day, where you just kind of zoom in closer and closer and closer. And we're not saying that the guy's foot rotated by 2,000 degrees in a second, but for a tiny, tiny part of that second, he was doing 2,000 degrees per second. I'm not saying he's going to go 48.5 meters. I'm just saying that in this little 1/10 of a second, that's what it looked like he was doing if I were to sort of zoom out and let him do that for a full second. Okay, and so you can play this game as long as you're interested in playing this game. Eventually, hopefully, you get some number that seems reasonable. Can we do just one more and really zoom in tight on this one? This one, I'm not going to write the details, but if we could get the average velocity, say, from 4.999 to 5. You guys check in with each other, just see if you can get a final number, run through the calculation again. So if you, the problem with doing any kind of rounding on this idea, on this kind of a question, is that the numbers are so close to each other that rounding could give you really, really big errors. You'd think, oh, I can just cut it off after the 100th place or the 1000th place, but the numbers are maybe the same up to the 100th place or the 1000th place, and you subtract them and you get 0 instead of some tiny, tiny number that's not 0. So without rounding, I've heard a couple of folks say 48.995. Somebody gave some good advice to one of their table mates. Try to type the whole thing in one shot. Like, see if you can get to the point where you're comfortable typing in long, complex expressions on the calculator. And then you don't have to worry about writing down all the intermediates and rounding error and stuff like that. Yeah, you could store numbers. Yeah, so yeah, if you want to do it in bite-sized pieces, store the numbers in the calculator. Good advice.
This reminds me a lot of it seems like it's heading.
Yes, heading towards a number. This particular one does not use E, but I like the idea of heading towards a number. What do you guys think? If I had to ask you to guess, what was the instantaneous velocity, not even in this little 10,000th of a second, 100,000ths of a second, but at the instant t equals 5? Do you have a guess looking at the trend that we're seeing with these numbers here? It sure looks like 49 to me. It was 44, then it was 48.5, 48.995. I feel like if we got closer in, it would get closer and closer to 49. And so I like Garrett's idea of, you know, sort of like continuous interest or something that approaches, like we're approaching some number, even if we never quite get there. Okay, so we'll take a quick look at a Sketchpad file. Sketchpad is some software that you can buy if you are so inclined. It's not free, so that's sort of one of the downsides of this compared to GeoGebra. But I had already made a lot of stuff on Sketchpad before GeoGebra existed, and I don't feel like starting over from that. So anyway, so here's our picture. The purple thing is negative 4.9 x squared plus 450. That was our height function. So the purple thing, okay, it's not the path of the ball. What is the path of the ball? It's straight down. Why does it look like it's going to the right? This is time here on the bottom. Time is passing. The ball is just going straight down, according to this. Can you guys see the curve is kind of flat up at the top? What does that mean in terms of the ball? It's not moving very much. You just dropped it an instant ago. It's not going very fast. But you can see, you know, if this were like sort of one of our zombie racers here, what was the strategy? Was go faster and faster and faster. All right, so I have here my fixed point, which was at 5 seconds, and the height was 327.5. It's right there. And then what was the first one we did? We went 4, was it just 4? Okay, so if I go to 4, close enough to 4, that's the varying point right there. What did we get for the height at 4? Was it about 371? Okay, so it's that number. But I'm trying to give you another connection here, one that we talked a little bit about with the zombies. What's that blue line called? It's secant line. And the velocity that we're interested in is the slope of that secant line. Did we get negative 55? That wasn't right, was it? Wait, did I move? Oh, the fixed point moved. That's not supposed to move. Let's try this again. Yeah, fixed point is supposed to say fixed. Thank you. All right, so we said 4 and something around there. And did we get like negative 44? Okay. And but you can see that it's still a secant line. It still hits twice, but I can kind of keep zooming in, zooming in, zooming in. Last one we did, I don't know that I'll be able to get as much. Well, that's pretty good. So that's at 4.9994, which is a little closer than the one that we just did. What's the slope of that line? Well, yeah, I mean, it's so close that with rounding, it just went to negative 49. And that blue line is really close to leaving secant hood and becoming a tangent. And the slope of the tangent line is what we're interested in. Okay, so that is that, and we'll come back here. We'll go to number 3. Lost track of our readers. Are we over to Chris now? 3. Good. Sure. Not no points. 1 point. Yeah. Okay, that's not a good definition, but it's good enough for now. We'll fine-tune that definition soon enough. Number 4, we go to Tiffany. What is average velocity? Good. And let's bring that thing down. A line connecting 2 points is called a secant line. Slope of the secant line is the average velocity. We'll go to Bubba for 5. What is instantaneous? It's slope of the tangent line. I think those 2 things right there are the most important things for today. Instantaneous velocity is the slope of a tangent line. When you're ready, we'll try the next page. Okay, number 6, and you are Andy. Okay, so instead of going between 5 and 4 or 5 and 4.9, we're going to go from 5 to some arbitrary, some varying thing. So between 5 and t, well, we used to do s of 4 minus s of 5, right? Now what are we doing? S of t minus s of 5. On the bottom, it used to be 4 minus 5. Now it's t minus 5. It looks exactly the same as the calculations you just did. But instead of having a specific number that's near 5, we have t, general number. Okay, s of t, what do we do? Well, it's the formula. I mean, we have the formula for s of t, right? You guys buy that the s of t formula we wrote is exactly that in the parentheses? All right, s of 5, we did that a bunch of times. That's a number, it's 327.5. And then on the bottom, let's see, so it's a change in time. How much time elapses? Well, it's not a number, but it's whatever the difference is between t and 5. Okay, up on top, we can combine, yes? 450 minus 327.5, turns out that's 122.5. On the bottom, we have that, that's all we have. I've got a picture that should look familiar. It's just a static version of the thing we looked at a minute ago. And anyway, we have this formula here that the average velocity between t seconds and 5 seconds is given by that fraction right there. Okay, so now that we know, let's go to B and we'll go back to Sam. Yes, please. Okay, I'm going to do this kind of quick on the calculator. If you're like familiar with all the commands I'm using, you should be able to do it along with me. If not, what could you take a look at after class? Video, where you will see all the buttons because you're going to see the mouse, and you can do this later. And if you really just want to put your calculator down now, that's totally fine. I'm typing this thing into my y equals. Don't forget parentheses upstairs. Negative 4.9 t squared. I don't have a t, I have an x. Plus 122.5. What comes next? Parentheses divided by what comes next? Parentheses. I don't have t, I have x minus 5. So I'm typing this into the y equals. I'm not going to graph it, but if I did, would I see the picture that's sitting behind the screen here? What does that formula right there represent? That's an average velocity formula. It's not the height thing. I'm not going to see the height graph. I would see an average velocity graph. It might be interesting to take a look at. Try it later on. What I am interested in is going into table set. And again, what we want to do is ask, because we're going to plug in some very specific numbers for t. What was the first t that we plugged in? We plugged in t equals 4. Then we plugged in 4.9. Then we plugged in 4.99. I want specific numbers, so I want the calculator to ask me what I'm going to plug in. So don't worry about the numbers up above. They can be anything. I just need that to say ask on the independent line. Then I'm going to go into table, which is in the top right. So we go second, table. What was the first t value we plugged in? 4. What did we get as the average velocity between 4 and 5? Was it 44.1? Good. And what was the next t we plugged in? 4.9, and then we got, what was it, 48.5. That's way better. And then how many 9s did we do? Was it 3? Okay, now that's not quite the truth, but it doesn't have enough space to write the truth. If you go up and over, you see the truth. If you just highlight that, it's not negative 49, but it doesn't have enough space to write it all. Is this exactly what we wrote before? It isn't exactly? Was there a 1 at the end? Oh, we had a 1 at the end. Oh, Joe, you didn't tell us the 1 at the end. That's okay. Pretty compelling evidence that we're limiting towards that negative 49. Yeah, so if you're having any issues with like for some of us, we had some calculator typing issues to get that number before. Well, it sure feels like this is a safer way maybe to get the answer. Just do the work to get the sort of general velocity formula like we did here, and then type it in once. All right, let's go to C, and we're up to Todd. Okay, so notation that you might have seen in a pre-calculus class, but maybe not. This fraction right here should look familiar. It is the average velocity between t and 5. Here's the new part. To read that, limit as t goes to 5. Why does that make sense for what we've been trying to do? We were trying to get closer and closer to 5. The numbers that we plugged in for t here were 4 and 4.9 and 4.999, and we were trying to send those to 5. And so here's how we write it. Limit as t approaches 5. Yes?
Does it work the same way if you're coming from?
Good question. Technically, we shouldn't be convinced just by coming from one direction. We probably should have done like 5.001 and 5.01, and then maybe, I don't know, like 5. I mean, it's kind of anticlimactic because I'm getting further away as I go down, but at least they sort of meet in the middle someplace. Yeah, and in fact, the formal definition that we'll see is you have to think about both directions, and we better get the same number, and it sure feels like we are. That second negative 49, do you think it's really a negative 49? No. It's really a little bit bigger, well, if we ignore the negative. So those are my two numbers, and yeah, it sure feels like negative 49 is the right one in the middle. If we type in 5, why should we get an error? Yeah, we're dividing by 0. We can't do it. So it might feel like, well, why don't we just go to just do 5 right away? Because that's the one that we want. Why are we, sort of footseeing around this thing? You can't go 5. Okay, and then according to our estimate, what was that limit equal to? What was the instantaneous velocity? -49. Now, some of us may have some qualms about that. Equals. Did it actually equal? We made a guess, right? We made a guess that it was approaching -49, but I mean, in theory, it never gets there. But it is okay to write that equals. You're supposed to write that equals. Limit doesn't imply you actually get there. It implies you can get as close as you want. So we say it really does equal, right? So if there's any kind of funny business about it never quite gets there, it's buried inside of what that means. It's not buried in the equal sign. So don't give me like squigglies for it's approximately equal to. That limit is equal to -49. Okay, part D. Let's read part D. Are we now at Josiah? All right, I don't know why that's there twice. Oh, I do know. I think I retyped it using like an equation editor, and then I forgot to delete the second one, so we don't need 2 of those. All right, so what are we doing here? Well, we had our fixed point 5, and then we had this varying point t and s of t. It doesn't matter whether it's on the right or the left of the fixed point. But we're going to make a change. We're going to say, okay, instead of calling it t, some arbitrary moment in time by just going to the right from the origin, we're going to say, all right, how about we just kind of let 5 here be our standard, our starting point. And instead of going, from 0 to t, we're going to go from 5 a little bit to the right. And if I go h to the right, then I land on some new spot, 5 plus h. So h is going to be how far I go away from 5. It's not what t was. T was how long from the start of the experiment, right? We did t equals 4 seconds. T equals 4.9 seconds. We're going to call h the distance, the amount of time you wait from 5 seconds. So if we wanted to go, say, out to 5.01, how much is the h, which is how far you are from 5? Is it 0.01. So all we're saying is that h is how far away you are from the point that you actually care about. And we could have gone backwards too. What if I had gone, say, out here to 4.8? How much would the h be? -0.2. Let's go. 0.2 away on the left-hand side. It's analogous, right? It's just a matter of what are we calling the variable? Is it how long it's been since the start of the experiment at 0, or just how long has it been since the 5 that we care about? All right, so if we do that, I'm not going to fill in all the details. We're just going to jump to the answer. Instantaneous velocity is now. Our new average value calculator, new instantaneous velocity is. Okay, so I'm cognizant of the clock. I'm going to skip some of the details here. I just want to jump to this thing right here. Let's go to number 7. We are at Abby. Okay, I want to show you roughly where that came from. I'm skipping some of the details, but I'm hoping it's not too much of a leap. Here's what we had before. S of t minus s of 5 over t minus 5. Yes? Okay. An asymptote?
Yeah. Like where h approaches 0, there would be an asymptote.
I'm not sure what graph we're thinking about.
We only have a couple minutes.
Okay, but we can chat right after class. Yeah, I never thought about an asymptote for this kind of thing, but that's not to say it's not there. That's right. So upstairs, things change a little bit. All right, it's not that anymore. Instead of t, we don't have t. We have something like 5 plus h. Go a little bit away from 5. But then go ahead and subtract off the s of 5, just like we did before. That's what goes upstairs. What goes downstairs? It used to be you just subtracted the two numbers in the parentheses. It's still that. What do you get when you subtract the two numbers in the parentheses? You get h, which makes sense because from the beginning of today, it's been change in distance over change in time. How much time has elapsed in our new scheme? H. H is how much, that's what we defined H to be. How far are you from 5, the moment you care about? And so then hopefully it's not too much of a jump to say, all right, we don't need it to be S for some like position function. It could be any function. We'll just call it F. And then instead of focusing at 5, okay, I don't always want it to be 5. I'm just going to call it what letter? A. So A is my sort of generic, what moment in time are you focusing on? You see they're all in the same spots. And the H makes sense. It's on the bottom. That's how much time has elapsed. We subtract them. And then finally, if we really, really want to focus in on that one moment in time, what do we do with H? We send it to 0. Really, really small. And that's this limiting part in the front. Right? Okay, we're going to use this definition on the next page, so hopefully that will kind of clarify some of what we've done. Who's our next reader? Richard, can you do the note? Okay, the fact that it has a name means it's important. We're going to be seeing the difference quotient a bunch because it comes up every time we do this instantaneous velocity. Number 8, we'll go to Garrett.
Go back up to the zombie graphs and draw a tangent line graph.
Okay, so we've now seen tangent lines a bunch. So the first one actually maybe isn't the greatest one to start with because that one's sort of weird. But at t equals 4, and you guys, maybe you could use the bookmark as your straight edge, but you're just ballparking a tangent line at that one point. Okay, so I've drawn 3 tangent lines anyway, so they should all be uphill roughly, but if I could find the slope of that line, which I could estimate, what would that represent for Hertz? Instantaneous velocity. Remember I had said it's really hard to get numbers if you try to grab 2 points near each other and then do literally the change in distance over the change in time. But it's easy to estimate the slope of a line. Just draw it long enough. Don't draw a little tiny sliver of a line between 2 points. Draw the tangent line. Down here we've got Noether. Was Noether running faster or slower than Hertz at that moment? I heard a couple of each. Remember, the slope of the tangent line is the velocity. I feel like Hertz's slope is greater, more steep, than Noether's slope. So Hertz was running faster at that moment. And then Planck, another tangent line. And then the one that I skipped, which is kind of the oddball out, what is the tangent line? It's the line itself. Yes. So that is its own tangent line at every point. Okay, let's go back and we'll jump to the next page. And we'll go up to number 9. Ernie.
Talk about
So I feel like we've written this a couple of times. What does the slope of the tangent line represent? Instantaneous velocity. I'm sorry that we've repeated ourselves so many times, but I think that's a key thing. So we sort of sprinkled it throughout today's notes. Okay, let's take a look at 10. Tony. Second. Okay, So the whole without a calculator part is a little bit scary because we had to do a lot of calculations before. It must mean that the technique we're going to use here is not exactly the one that we did before, because I can't expect you to plug like 6.001 into a height formula like we did before, right? Okay, so first thing we need to do is come up with that height formula. So S of t equals. So it's the same thing that we wrote before. I'll write it again here. It was 1/2 at squared plus initial velocity times time plus initial height. A is the acceleration due to gravity. What is it in this problem? Is -32, because in this problem we're doing feet. So -9.8 meters per second squared, -32 feet per second squared. Don't forget that negative. Negative means down. So there's my t squared plus initial velocity. There's 100. It's given. 100 t plus initial height. 6 feet. 6. So we simplify 1/2 of -32, and we've got our height formula. Now, what we would have done before was plug in 5.99 or 6.001, but we're doing this without a calculator, so we can't do that. All right, let's give this a shot. We're going to use our new definition, the one with the h in it. I'll write it here. I'm going to do the difference quotient first, just abbreviate that DQ. So the difference quotient before, on the previous page, was S of A plus H minus S of A divided by H. Always has that form. The letters might change a little bit, but that's the difference quotient. A is the specific moment in time we are focusing in on. What is the number for A? It's 1. 1 second into the flight. So we're doing S of 1 plus H minus S of 1, and it's divided by H. Don't feel like we need to plug a number in for that H. That H is going to be with us for almost the entire problem. Okay, S of 1 plus H. Well, let's start with S of 1. That part's easier. Can we find S of 1 without a calculator? A couple of folks say 90. You good with that? All right, so that's 90. Just going to highlight the substituting that we've done. S of 1 is that. S of 1 plus H. This is tougher. In fact, I don't think I have enough room here. Equals S. No problem. So we plug S of 1. That means plug T equals 1 into that red formula. Okay, S of 1 plus H. That means all of the T's become 1 plus H. It's harder than plugging 1 in, but it's something you guys have seen before. So we're doing this. -16 times something squared. What's the something? Is 1 plus H. Plus 100 times something. 1 plus H. Plus 6. Okay, I'm going to do more highlighting stuff. That 1 plus H got plugged in for all of the T's. We did S of 1 plus H. Not as easy as just plugging 1 in, but it's the same idea. Replace all the T's with what's in the parentheses. What is that supposed to be divided by? H the whole time. Okay, now we have some algebra to do. We need to try to clean this thing up. On the top, I see a -16. 1 plus H squared. Is it 1 plus H squared? No. You have to FOIL. Write it twice. Okay, so make sure you don't do something bad there. Get a 2H in the middle. plus, we'll go ahead and distribute the 100 there. 100 plus 100h. And then we'll combine. What do we have at the end? 6 minus 90, negative 84. Still divide by h. You know how you take like 5 years of algebra? Before it changes names, but before you take calculus, you got to take like 1,000,000 courses in algebra. All right, so we're going to be using the 1,000,000 courses in algebra throughout the semester. Here's part of it: is the ability to take, to simplify complicated-looking things like this. What comes next? Distribute that negative 16. I'll go ahead and combine some more. I have 100 and I have a negative 84. So that's a plus 16. And then a little more simplifying. What happens? 16s cancel. That turns out to be quite fortunate. So I'm going to write negative 16h squared. How many h's do we have? We have negative 32 h's plus 100 h's. What is that? That's 68. And we're going to simplify just a tiny bit more. What can you factor out on top? Factor out an h. And if at that final stage you can factor out an h, it means you did it right. If you can't factor out an h, there's a problem somewhere. What can we do now? Yes, this is the most satisfying part of the problem, because from the get-go, what did we want to send h towards? 0. We want h to be really small, 0. Can you plug h equals 0 into any of the previous versions of this fraction? No. Can you plug h equals 0 into negative 16h plus 68? Yes. That's why we needed to cancel. So apologies for going over it. Last thing we need to write is this. Limit as h goes to 0 of that guy. What do you think you get when you plug 0 in for that h? 68. 68 feet per second. Is this grapefruit going up or down? Up is positive. It is still going up. I gave it enough velocity that a second in, it's still going up, but not as fast, and eventually it will come back down. Sorry for going over. Homework is right there at the bottom. And again, check out the video if you need to see any of the details on that algebra on the last problem. Have a great weekend.